Hello, welcome to this next exercise. Here we're looking at a two-factor ANOVA called a factorial design. This is a little bit different than the other ANOVAs that we've done because now we are opening the door to the possibility of testing a set of hypotheses across two factors. And within each of those two factors, we have then multiple treatments. So we're going to be doing a few things here. We'll have not just one, but three sets of hypotheses. So up until now, we've had something that looks like this. Not all are equal. And with a set of hypotheses like this, it was implied we were looking at just one variable, one factor of investigation. And we're testing for equality or differences across those three treatments within that one factor. But now we'll have another factor of investigation, and within that factor we can have as many treatments as we want. In our examples, we'll keep it to 2 because, again, that just helps keep the calculations short and a little bit faster to get through. So we'll have something like this, and given that we only have 2 treatments within that second factor, that's the only case where we can write the alternative like this. If you want to be very thorough and consistent, you would say, again, not all are equal, but again, we only have that one pair, so there's not really much opportunity for there to be any other sets of differences. So we have our 2 sets of hypotheses testing for equality across treatments in each of 2 factors. But now there's also going to be a third set of hypotheses. I'll write it in at the top here. And that is a test for what we call interaction. And so here we'll just write this out like this: no interaction. And interaction exists. And what this means is we're going to be testing also to see, are there specific combinations of treatments that have statistically different results than other combinations of treatments. So in this design, in this ANOVA, we're going to have these 3 sets of hypotheses. So we'll have 3 F statistics, 3 p-values, and 3 critical values. So we'll have a whole range. We'll have 3 different sets of conclusions now. So let's get into this exercise, and then we'll talk about issues as they arise. So here we're looking at a local animal rescue shelter is interested in knowing if there is a significant difference in the number of animal adoptions between its 3 largest shelters during its busiest weekend of the year. It is also interested in knowing if there is a significant difference in the number of cats and dogs adopted as well. The following data shows the number of each animal adopted at each of its 3 shelters on each day of a long weekend. So here we have our first factor. Let's call this our first factor, factor A. And within factor A, I have 3 treatments, A, B, and C. So these would be our 3 regional shelters. And so there's going to be some new notation in here. It can be a little bit tedious. So if I call this one factor A, capital A, then I have, for the number of treatments in previous exercises, we used K for the number of treatments. Now I'm going to use lowercase a for the number of treatments in factor A. So that corresponds to this set of hypotheses here, where I have those 3 treatments in the null hypotheses. Factor B is this one out here, where I have the dog and the cats. And so within factor B, here I only have these 2 treatments, and so this is going to be that set of hypotheses for factor B. Now you'll notice in this data set that I have, there's a lot of means that have been calculated. Now I've calculated these just to help speed up this video. I don't think I need to explain how to calculate all of the means all of the time, so I've just added them to the data set to help speed this up. So what we have here, many of them are similar to what we've had before. These are treatment means. So this would be the mean of all of these observations for dogs across those 3 treatments in shelters. Here, this is the treatment mean for all of those observations for cat adoptions. So we've got those treatment means across treatments in factor B. We also have treatment means for those treatments in factor A. So that's going to be the mean of these values here. I'm just excluding this one. It's all of these numbers, excluding those means. So those are the treatment means, just the means of the observations. These interaction means that I've got in here, these are the means that correspond to the average for the observations between two treatments. So let's say this one, this 3.0, this is the mean of these three observations. 1.3, that's just these three observations. 2.3, that's these three observations. And we call these, this is going to be R, which is equal to 3. R represents the number of observations per treatment combination. So for the number of dog adoptions in shelter A, I have 3 observations. The mean of those 3 observations is 3. For the number of dogs in shelter B, I have 3 observations, and the average is 1.3. Okay, so there's a lot of different means going on here. When you're dealing with a problem like this on an exam or something, what I would suggest you do is calculate the interaction means first, because each of those is just the mean of the replications, so it's the mean of the 3 numbers. And then for the treatment means, this treatment mean would be the average of these 3 interaction means, or, as is longer, and as I said before, you could take the mean of these 9 numbers, but it would be faster just to take the mean of these interaction means. This one too can be the mean of these interaction means. When you're calculating these treatment means for factor A, these ones here, that would just be the mean of these 2 interaction means. So there's some shortcuts in calculating all of these means. You can calculate them just from the raw data itself, but when time is an issue, I would suggest calculating the interaction means first, and then from there you can calculate the treatment means. And then, of course, we have the grand mean, as we've always had for any ANOVA exercise that we've done. Okay, so let's get started on some of the calculations here. The process is going to be very similar to what we've done before. Here again, we are partitioning the total variation in this data set into its different sources. Now we have 4 different sources. We have the variation that is due to treatments across factor A, plus variation that is due to treatments across factor B, plus variation that is due to interaction between those two factors, plus finally random variation in that data set. Can you hear that funny squeaking sound? I've got a dog with a teddy bear. It's one of her favorite new toys, I think. Okay, so if we go through the formula, I'll just write them out. Where can I write them out? I'll write them out up here, actually. So SST, again, SST, this is the total variation in that data set. Now, this formula can look tedious because I have on my characters, I've got 3 subscripts now. So this, it's still just the difference between individual observations and the grand mean squared. But now we have this triple summation, which my students hate seeing these, because I have now 3 subscripts denoting different pieces of information. I is equal through 1 through A, so that's across treatments in factor A. J is 1 through B, and K is 1 through R. So that's just going across each replication. So what I mean, if I look at this observation in here, this would be observation 2. Change that, observation dog in shelter B, and it's my second observation, or my second replication. All right, this one down here, this is observation dog, shelter C, replication 3. Okay, so again, there's just all of these different subscripts denoting its position within the data set. Oops. The calculation itself is no different from anything that we've seen before. It just looks more tedious. Okay, SSA, so this one is going to be similar again. Here we are looking at treatment means in factor A, and we are adding those up across all of those treatments in A, and we multiply it, as always, by the number of observations contained in that relevant treatment. In this case, we call it BR. Why BR? Well, in factor B, I have two treatments. I have 3 replications. So each of these treatment means here contains 6 observations. 2 times 3. So it's still the same calculation that we've done before. It's just the notation starts to look a little bit more tedious. Let's see, SSB. This is going to be very similar. We're looking at means across treatment B, differences from the grand mean squared. We add those up across all of those treatments in factor B, and we multiply it by A times R, which again is just the number of observations in that treatment. So this treatment mean in factor B, it contains 9 observations. Well, that's just 3 times 3. So again, same calculations. Notation makes it look a little bit tedious. The next one, this is the one that my students like the least, I think. SSAB. Now this one here, we're looking at, we have our interaction mean, so this is IJ, minus the treatment mean in factor A, minus the mean in factor B, plus the grand mean, all squared. And this has a double summation. I equals 1 through A, J equals 1 through B, and we multiply it by R. So here we're looking at these 9 different interaction means. And so for this notation is simply saying, well, this mean here, let me pick this one. This is the mean for IJ, so it's in treatment A, in factor A, and it's in treatment cats, say AC. So this is the mean for treatment A in factor A, right? It's in this treatment, and it's in this treatment. So it's the combination of those 2 treatments that gives us that interaction mean. Okay, so now let's get into our calculations. We've got a big ANOVA here to fill. So this is going to be factor A. Let's put in the names actually instead of just SSA or SSB here. This is factor A is the shelters. So this is the shelter. In brackets I'll put A. Factor B, this is the animal, dog or cat. This is interaction. This is error. Oops, one too many R's in error. And this is our total. Now, once again, because we have so many factors, or so many treatments, we can no longer calculate SSE from the data. So I've actually cheated. I just have to bring it up on my other computer. Similar to our randomized block design, in order to obtain SSE, we are going to need to have SST. I'll never ask my students to calculate SST. It's too time consuming. So we can calculate SSE by the difference between all of these, minus SSAB. And then, of course, that information, or the SST is given to you, and so you can easily calculate SSE. So I forgot to put it on my notes, but I've got SSE, sorry, I have SST is given as 25.6. is my SST. So I'm going to have to add that into my SST is 25.6, and then we'll use that to obtain SSE in the end. Okay, so this video is already 15 minutes in and we haven't even started on the calculations yet. So let's get into that. That's probably going to add another 20 minutes to this video. These ones get longer. I'll completely understand if you want to fast forward all of these calculations, because I know it will be a little bit tedious, especially the interactions, probably the slowest one. So let's start with SSA. So here I'm going to be using this formula here, and we're going to be using then these three treatments here. So SSA is going to be B times R, so that's 2 times 3. And now these three treatment means 366 minus 2.72 squared plus 183 minus 2.67 squared plus 267 minus, oops, I made a mistake right there. That's 272. 267 minus 272 squared. Okay, so let's get a calculator out here. There we go. Okay, so open brackets, 366 minus 272 squared plus 183 minus 272 squared plus 267 minus 272 squared equals 167, and I'm going to multiply that by 2 times 3 is 6, so times this by 6, and SSA I have is 10 point, let's call it 10.1. So here I have 10.1. Degrees of freedom on SSA is A minus 1, so the number of treatments, again, this part's very similar, the number of treatments minus 1, so this is going to be 3 minus 1 is 2, and so our degrees of freedom here will be 5.0, our mean square for factor A is going to be 5.05. Now let's go on to the next factor, so SSB. Let's change our color here. SSB. So we are now going to be using this formula. So A times R, so that's 3 times 3. And now I'm looking at these treatment means here, which are means across factor B. So 2.22 is our first. I'm going to scroll down a little bit. 2.22 minus 272 squared plus that second one, 3.22 minus 272 squared. This one will be nice and easy, nice and short at least anyways. So here I have 2.22 minus 2.72 squared plus 3.22 minus 2.72 squared equals 0.5, and then multiply that by 3 times 3, so multiply that by 9, 4.5. Perfect. 4.5. Now our degrees of freedom here, this is just B minus 1. So B minus 1, I had only 2 treatments there, and so this is going to be just 1. So mean squared error, here's this 4.5. Okay, good. Now, moving on, here I'm going to go up to interaction now. So interaction, this is going to be this awful one here. Awful. It's long because we're looking at our interaction means, and here I have 1, 2, 3, 4, 5, 6 interaction means. So there's 6 of these things we have to square and add together. So this one might be a little bit longer. So we multiply by r, which is our number of replications. Here is just 3. So 3 times. Now, let me see if I can fit all this in. Hopefully I don't have to scroll up and down too much. So this is 3. So hang on, I'll trace my steps here. So this is going to be this one here. Subtract out its 2 relevant treatment means. So that's what these 2 treatment means are here. So 2.2 and 3.6. 2.22, 3.66, and then add back that grand mean 2.72 squared plus. Now the next one is 1.3 minus. So still this same treatment mean here, 2.22, but now this treatment mean minus 1.83 plus the grand mean, always 2.72 squared, plus, I'm going to have to scroll down, I think I'll run out of room. Now 2.3, oh, I'm going to scroll up, 2.33 minus, now we're still in that same treatment in factor B, so it's still 2.22 there, 2.22, but now we're at this treatment mean, 2.67 plus our grand mean, 272 squared, plus, now we are down to these means here, so 4.33 minus, now this is our relevant treatment mean across factor B, so minus 3.22 minus, and this one here, 3.66 plus 272 squared plus 2 more still to go. So now we're up to this one, 183 minus 3.22 minus 1.83, where am I? Oh, I made a mistake. Sheesh, I don't want to do that. We're at this one here, 2.33. Let me just make sure I haven't. Okay, no, we're okay. 2.33 minus 3.22 minus this one, 1.83 plus. Now we're at the very last one here, this one, 3 minus 3.22 minus 2.67 plus 2.72 squared. And I just noticed back here I forgot to add in 272 squared. Oh boy, these are time consuming to calculate. And because they're time consuming to calculate, and I'm already 23 minutes into this video, I'm going to cheat because I happen to have the answers on my computer screen right beside me. So I'm going to cheat on this calculation because that'll take me far too long. Hopefully you can crunch through those calculations, and here I have it, 3.33. Sorry, that's not fair that I get to cheat, is it? And so here we have our degrees of freedom as r minus 1, number of observations, number of replications, minus 1. We had 3 replications, so I have 2 degrees of freedom, and 0.33 divided by 2 is 0.16 or 17, we'll say. Okay, we're doing all right. Let's fill in SSE now. So SSE, again, we're going to use this relationship right here that we have here. So I've already been given SST. We calculated the rest. Well, I sort of cheated on interaction, but we calculated the others. And so now I'm going to just pull up my calculator, and I have 25.6 minus 0.33 minus 4.5 minus 10.1. and I have 10.67 for our error. Now the degrees of freedom for error is a little bit different. This one is A times B times R minus 1. So the number of treatments in A times the number of treatments in B times replications minus 1. So I have 3 times 2 times 3 minus 1 is 2, so that's 3 times 2 is 6, times 2 is 12. So 10.67 divided by 12 to give us our SSE divided by 12 is 0.89. Okay, now just for completeness, degrees of freedom on SST is always NT minus 1, which is also going to be the same as adding up all of our degrees of freedom that we have above. So this is still going to be, this will be 18, 12, 14, 15, 16, 17, not 18. I have 17 observations, degrees of freedom 17. Okay, I hope everybody's hanging in there. This is going into a long video. We're going to be half an hour by the time we're done. So our F statistics now. Now we have 3 F statistics. And these 3 F statistics, let me grab another color here. We're running out of colors. So I'll have F statistic on factor A is MSA, so that's mean squared for factor A, divided by MSE. The F statistic for factor B, MSB, divided by MSE. And for interaction, this is MSAB, so this is here AB, divided by MSE. The one thing to note here is that MSE is always in the denominator. It's an easy mistake that I've seen students make. They get those all these MS, mean squared things mixed up. It's always going to be MSE in the denominator. So for this first one, this is going to be 5.05 divided by 0.89. The next one will be 4.5 divided by 0.89. And the next one, interaction, will be 0.17 divided by 0.89. So if I get our calculator out, I stand corrected. This is going to be more than half an hour once I'm finished. So here's our first one, 5.05 divided by 0.89. So 5.67. There's 567. Our next one for MSB, 4.5 divided by 0.89 is also 5.05. Our next one is 0.17. Oops, what happened there? 0.17 divided by 0.89, so 0.19. Oops. Okay, so now we have our 5 test statistics, and now we need 3 p-values and 3 critical values. Let's get the critical values first. We'll do all of these tests at the 0.5 level of significance. Now we'll have 2 of our critical values will be the same, but one's going to be different. If we look at the critical value on the test across shelters, that one has 2 degrees of freedom. Let me grab my highlighter. This one has 2 degrees of freedom in the numerator, 12 degrees of freedom in the denominator. That's going to be the same as the critical value for interaction, which has 2 degrees of freedom in the numerator and always 12 in the denominator. For factor B, that one's going to have just 1 degree of freedom in the numerator. So we can't always assume that we'll have the same degrees of freedom for, the same degrees of freedom for all of our tests. They may, all 3 of them could be different. It's possible they're all the same, but we can't assume that they'll always be the same. So let's do the first one. So 2 degrees of freedom numerator, 12 degrees of freedom denominator. So here's, So here is 2 degrees of freedom numerator, And I think right at the bottom, I've got 12 degrees of freedom denominator. Alpha is 0.05. And so if we track this down, so I have 3.885. And that's going to be my critical value for both 3.885 for both factor A and interaction, because those two both have 2 degrees of freedom in the numerator, and they all have the same degrees of freedom in the denominator. So the critical value now for factor B, so I have to go back to our F tables. Now I have still 12 degrees of freedom in the denominator, so my denominator degrees of freedom don't change. But now I have just 1 degree of freedom in the numerator. So now we're just going to come down this row, and here's that critical value, 4.747. So this one is 4.747. Might as well get p-values while we're looking at our tables here. So the first, let's go back one at a time. So the first one, 567, from a distribution with 2 degrees of freedom and 12. So let's look for 567 first, and that's in this 2 degrees of freedom and 12. So 567 is in between these two values. So that gives me a p-value in between 0.025 and 0.1. So this one has a p-value between 0.025 and 0.01. And that's, while we're working with that same distribution, let's look for this one, 0.19. So that's also in that same distribution. And 0.19, well, it's smaller than the smallest. So that p-value is going to be something larger than 0.1. So this p-value is going to be larger than 0.1. And finally, on the animal factor B, so this is a test statistic 5.05, and we're looking at a distribution with just 1 degree of freedom in the numerator, still 12 in the denominator, so that's coming back to this one here. And our test statistic was 5.05. 5.05 is somewhere just right in here. So that gives me a p-value right in here between 0.025 and 0.05. So here, this p-value is greater than 0.025, but smaller than 0.05. Okay, that's it. That's the complete ANOVA. My goodness, I'm over half an hour. I don't know how you've lasted this long. So now we can draw our conclusions. So if we come back up, our first test on factor A, we were testing across the equality of the number of adoptions across these 3 shelters, these 3 regional shelters. What was our conclusion? Our p-value is less than 0.025, so it's less than alpha. So on this test here, we can reject. We do have sufficient evidence to show that there is a difference in the average number of adoptions across these 3 shelters. I think this was just over a long weekend. So there's our first set of conclusions. The next one, again, our p-value is less than, oops, that was a horrible, they were less than 0.05. So again, that's less than alpha. And we can see up here for factor B then, we also reject on factor B. And so there is a difference in the average number of dogs and cats that were adopted across this long weekend. So we do have evidence to show that the average number of dogs and the average number of cats is different. The numbers adopted is different. So we rejected on both of our factors. If we look at interaction, our p-value there is greater than 0.1, so we do not reject. So for this one up here, we do not reject here, so we have no interaction, meaning there's no statistical evidence to show that there's any particular combination of treatments that is statistically different. So here we're looking at comparing across these 6 means. There's no statistical difference across those 6 means. Okay, so that's it. 35 minutes. My gosh, longest video ever, I think. So hopefully that all made sense. We can go through and apply the critical value approach to all of these tests as well. I won't go through it in much depth. Let's just look at these two here, for example, because they both have that same critical value, 3885. And here we can see 567 is way out here, so that one corresponds to a reject. And this one was 0.19, so that's somewhere way in here. And that corresponds to do not reject. So we can apply a critical value approach, p-value approach, either one of these is perfectly fine. So I hope that all makes sense. It is a long and tedious process. I hope you don't hold any grudges that I kind of cheated on this calculation, and I just noticed this should be SSAB for that formula. It is long, it is time consuming. This video would be 10 minutes longer had I not cheated on that one. So again, hopefully you made it through this whole video. Thanks a lot for watching, and we're going to do at least one more. Okay, bye-bye.